Okay, it's Paul here, and I thought we'd have a little fun today and do something a little different while I'm sort of in between projects. Always have a lot of projects around, but I got this idea and to develop a variable DC power supply. You ask what's so different about that idea. Everybody has DC variable power supplies. Well, not so. I have a limited DC power supply. It doesn't produce much current. It's not very efficient for working on tube radios, for sure. And then I have some 1 amp power supplies, but they're 5 volt and 12 volt respectively. They really don't have variable voltage per se. I could fix that by doing what I'm about to do here, but I wanted to show you this because I think it'd work better for tube radios, especially tube radios that use AC or DC, the older models. So what I did is I got on eBay, and let's see if I can pull this up real quick. I got on eBay and I ordered a lot of some new diodes. They're 1N5404. 1N5404 diodes. They're rated at 3 amps, 400 volts. And I got these for a pretty good price. I think I got 10 for $245 or something like that. I don't know. And I think it was free shipping. Yeah, free shipping. Anyway, I bought these diodes, and this is them here. And like I said, they're rated at 3 amp, 400 volts, which is plenty for what I'm going to be using them for. And what I'm doing is, you know, and most of us who work on tube sets, we have a power supply. Usually we have a Variac with an isolation transformer, and that's what I have. So what is a 3 kilovolt isolation transformer that's driven by a Variac. And that Variac controls the voltage of the isolation transformer primary. So just to give you a pictorial image, I have a Variac. It goes from 0 to 140 volts. Okay, that Variac drives the primary of my isolation transformer. The secondary of the isolation transformer is a 1-to-1 match. This is a 3 kilovolt amp, 3000 kVA transformer. It weighs about 50-something pounds. And what I did is I took that and I'm feeding it into a diode bridge, full wave rectifier. So what that gives me is I get a ground wire here, and I get a positive wire here. And so, since this is a 1-to-1 and it's driven off my Variac, I have a variable speed, full wave rectifier made out of those diodes that are rated at 3 amps and 400 volts. Okay, so if I connect, but if I take my scope, which is plugged into a grounded outlet, and I put the neutral here. This jumps up to 130 volts, somewhere around there, AC, which makes no sense because I'm totally isolated, but it does. And what's happening is this transformer, being a gigantic transformer, is just coupling in with all my bench equipment. So that's just coupling voltage that'll show up, and I'll demonstrate that in a little bit. But that goes away if you take this and you tie a load in here. Then if you measure the voltage across here, you have no AC. You just have pure DC, and it's no longer ridiculously high. I was getting high DC voltage readings with my Variac at 0 and the switch on. Basically, there's a switch, there's a current limiting bulb here, which is switched out for this particular circuit. So I still had some ripple and stuff like that, so I put a electrolytic capacitor in here to ground. So this would be the ground side, and I put a 10 microfarad 450 volt capacitor across the line, and that gets rid of all of the ripple and any stray induced what you call ghost voltages. They're there, but they're like, you know, a billionth of an amp. I mean, they just show up as voltage but no current. Well, this gets rid of that, ties it down, as well as the load resistor, which loads the system down. So this is the schematic, and that's using, can't get to them, that's using those diodes that I mentioned that are rated at 3 amp, 400 volts. So if you're familiar with a full range rectifier, you can see what's happening here when you have a sine wave going in, right? This is the circuit, and that's the way it's hooked up. Okay, so let's look at it. And I'll show you what we got. All right, I got a line cord, has a switch on it here, and I'm just suicide connecting it to my Variac power supply, and got a 100k ohm resistor here, 1/4 watt, little tiny guy. That's my load. So what we're going to do is we're going to run the AC in here, and we'll get the DC out here. So this is the negative, and this is the positive. And I'm going to redo this so it makes a little more sense to you people. I just threw that over there. So if we run this here to the ground line, that's the negative line, and we run this one over here to the positive line, and I'm just going to run that way. So the output of this bridge rectifier is now across these two runs. These are all negative. Excuse me, these are all positive. That's my DC coming out. So I'm going to put my load across the end here. So the DC is right across the load, right? And I'm going to put a filtering capacitor in the line, over here to get rid of any ripple. Okay, so that's the circuit. Now if I take my meter and I connect it to some wires for make it easier to use, some jumpers. I want to stay on today. Must be because it's cold and my fingers are cold. Okay, so we're going to put this first across the AC line. So we're going to measure the AC coming in. Okay, so I'm right across the AC coming from my Variac now. So if I put this on AC, there, and I turn on my power supply, you see that immediately I have 0.352 volts of AC coming into this rectifier circuit. If I bring the voltage up, you see it goes up as I bring up my Variac. Okay, so here's step 2. I'm going to take my scope and I'm going to plug it. Well, actually I'm going to connect the ground to the ground side here, but first I want to set this back to DC. So I'm going to disconnect the meter from here and go to the DC, directly to the DC, and we'll measure it across this load resistor for now. So this is the negative side of the DC. This is the positive side of the DC. Get up a little bit away from the other one. Okay, so we go to DC. You see I have 0.11 volts DC. If I bring up my Variac, I have available DC power supply. Okay. Now, this is where it gets interesting. I have my scope turned on. I have it set on DC. If I take out this capacitor and I take out the resistor, the load, and I just put this across, actually let me use these to do it. If I just put these across the output of the bridge rectifier, there and here, so this is my voltage output right across the bridge rectifier. You see I have 10 volts DC. That's with the Variac set at 0. I already have 10 volts, so there's a problem there, right? And if I turn it up, you see it does go up, but the voltage is not correct. This is a ghost voltage. This is not a real voltage. I just showed you that the voltage started at around 1 volt. I have no capacitor, no load. Okay, if I take my probe of my scope here, and I'm just going to connect it to the same ground there. Look at the voltage. 109 volts, 110 volts DC. I haven't done anything but connected the ground of the scope to the ground of the output of this bridge, and I already have, according to this, 110 volts DC. Of course, that's impossible. And if I take the positive of the scope and put it in the terminal, you see it drops to 86 volts DC. It says I have 79 volts AC. Well, there's no way I have 79 volts AC because I'm going through a bridge rectifier of diodes that do not allow AC to pass through. So I have 80 volts of AC and 87 volts or 86 volts of DC. Impossible. Those are ghost voltages. Now, if I'm going to leave my scope attached here, I'm going to leave these attached the way they are. I'm going to put the capacitor back in. I get it in there, and you'll notice that it's charging the capacitor to 100 and something volts, 105 volts. So there is a voltage there that should not be there, but again, it's an induced voltage by the isolation transformer, which I'll show you in a little bit. I'll show you the system, and the mains of the scope, even though they're totally isolated. So this is something to be aware of. Now that voltage is, again, a ghost voltage. It's there, it's real, it's charging this capacitor, and all of that is actually happening. But it is still a ghost voltage because it has no current capability. Right now, if I bring the voltage up to where I can see the current on my meter, I have 20 milliamps of current. 0.5 watts is being consumed in this circuit to keep that capacitor charged. But if I put my load in here, watch what happens. I'm at 42 volts, and that's where I am on my Variac. If I go down to 0, it takes me down to, well, the capacitor is discharging, to give you an idea, but it's down to 3 volts. Now you remember, without the load, as soon as I turn down my Variac, my system, this went to 10 volts DC. When I plugged in the scope, it went to an outrageous amount. If I take my scope now and put it across there, no change. No change at all. It's accurate, because this resistor is now loading down the system, and all those ghost voltages are disappearing. They don't really exist anyway. I mean, they're there, they're induced in the wires, they're induced in the scope probe, they're induced throughout the air with electromagnetic field being generated by the isolation transformer. Remember, I have a 3 kilovolt isolation transformer. That thing weighs just under 60 pounds. I think it's like 58 pounds. Now, I'm not using 3 kilovolts. This is a 1 to 2 or 1 to 2 transformer with center taps, and goes from 120 to 240. I'm not doing that. I'm using 120 and half of the 240. I'm using the center tap off the 240 side. So I'm putting 120 to 120, which is 1.5 kilovolt amps. That's the most I can get, which is fine because my Variac's only rated, I think, 5 amps. So I can only do so much. I can't overpower this or use it at its full potential. I also have a 5 amp fuse in line here. So that's where we're at. But with the capacitor and the resistor, which, by the way, is nice and cool, and it's only a 1/4 watt 100k ohm resistor. I chose 100k ohm because of the calculations come out fine. So if I turn this up to, say, 100 volts, and it's getting there. Okay, roughly 100 volts DC. Right there. About 100 volts DC. I'm actually putting out of my Variac, and this isolation transformer across here, I'm putting out 72.2 volts, and I'm receiving here 100, so 72.2 volts AC going in, 100 and volts coming out across the capacitor, across the volt ohm meter, across the scope, well actually just tied to the scope, but doesn't matter if I go across the scope, it ain't gonna matter. It just shows up the voltage on my scope. And it doesn't change it, but a few percentage. And anyway, so I got 100 volts. Well, if I have 100 volts over 100 k ohm resistor, okay, I had a little problem with a switch on the wire I was using. It was throwing off some stuff. So I'm going to kick that back up to 100 volts. Okay, so we got 100 volts going across there. That would be 1 milliamp of current going through a 100 k ohm resistor. 1 milliamp, or 0.001 times 100 volts would be 0.1 watts. So it's using 1/10 of a watt. And the resistor is not even warm. Yeah, it's got a little bit of temperature to it, nothing really, because it can stand 0.25 watts. It's a 1/4 watt resistor. So right now, 1/10 of a watt is going through it. So let me show you what my system consists of. Okay, so this is my system here, which you see me, this is the circuit here, which you've seen me set up. And we're at 100 volts. And to get that 100 volts, I'm putting in 72 volts. So I've got a 30 volt gain here with this full wave rectification, because this is, well, it's actually 72 volts RMS. So if we have 100 volts coming out, and this is my isolation transformer. That's the 3 kilovolt amp isolation transformer. You can see it's a big boy. Got big old heavy wires on it. I've got, well, I have a light for checking current limiting, and I have a Variac that drives the input of this. So the Variac drives the input, which drives the output. So right now it's putting out 72 volts. There's 0 current going through the system. It's very efficient. There is current going through it, but this meter doesn't measure that low. And so we got no wattage to speak of, not even 1/10 of a watt. And, you know, less than, well, we got 1 milliamp, so it's not going to show on that meter because it starts with 10 milliamps. And that's what this would require. And that's the circuit. So we have the potential of voltage. If I crank this up to 100 volts, which I can go all the way up to 140 on this. But if I drive that up to 100 volts, it's 101 volts, I have 140 volts DC. If I drive this, well, of course now this resistor will start getting warm because I'm getting close to the current limit of the resistor. It might pop. If we drive it up to 124 volts there, we have 172 volts DC. And this system is able to put out well over an amp. So that's quite a bit of power. Right now we're putting out 0.3 watts, 0.4, 0.3, so about 3.5 watts. And 120 volts and sustaining 173 volts DC. Capacitor is nice and cool, having no problem smoothing that out. And we've got a good signal, a good amount of heat on that resistor. So let me drop it down and we'll drop it down to cool off the resistor a little. Okay, I'm at 50 volts, 51 volts. So if I turn on my scope again, and we go ahead and hook it into the circuit here, connect the ground to ground. Actually, I'll connect it to this ground, and the positive of the scope. Oop, we had it for a split second there. Positive scope can go right into the terminal strip. And we're on ×10. So if I go to, there's my ground reference. I'm on ×10, I'm on 50 volts per division. So you see, we're at right at the center line. If I turn this to DC, you see it jumped up just a little bit over 50, over one thing. Actually, it's showing about 70. And that's what we got, 70 volts DC. So as I raise my Variac, the voltage goes up. So you can see it climbing there. So that's 100 volts, 107. So it's about 2 divisions, smidgen over. And if I bring it back down, you see the voltage drops accordingly. So I have a power, and I'm on 0 there, and you see it's zeroed out. If I raise the volts per division to 20, then as I crank this up, you see it go up a whole lot faster. Right there, we're up to, 3 divisions, 60 volts. I'm showing 63 volts DC. And so, by doing this, by running through this bridge rectifier, full wave bridge rectifier with a smoothing capacitor, I have that kind of DC voltage coming out. Very good, very smooth. Got just an unbelievably small amount of ripple there. And here's the ground reference line. So you see I'm not right on it. That's why the numbers weren't exactly the same as my voltmeter. No AC at all, pure DC. And that's thanks to that capacitor. If we take the capacitor out of circuit, it's kind of hard to do 100 volts on there, but we'll do it. Take the capacitor out of circuit, the voltage dropped to 40, and now we should have some AC ripple, and there you go. So, let's see if I can get that better. There's the AC ripple on the DC voltage. But that 10 microfarad capacitor is more than enough to get rid of that ripple. And I don't want to get shocked, so I'm doing this while I'm holding the camera here. Okay, ripple's gone. So back to DC, straight DC voltage. And this will drive it'll drive an amp easy. Drive it probably close to 2 amps because you got 2 3-amp diodes. So the 3 amps are the maximum on the diodes. So for each side of the waveform, when this one's negative, this is negative, this is positive, goes through this one to this one. When this is positive, this goes to here, and this negative one, part of the cycle goes here. So you always got, you're basically flipping the wave. And I will show you that on the paper here again. So the system shut off now. The capacitor is discharging. So when the waves go in positive, this diode is forward biased, so positive goes here. This diode is forward biased, so this one, so the negative is there, so you got negative there, positive here. When the wave goes negative, just the opposite. This one's forward biased, so the negative goes there. This one is now positive biased. Current travels through this diode. So it's always going through two diodes. So, but the diodes are rated at 3 amps. So the most I can drive through this is 3 amps. More than I'll ever need for a radio, because the radio runs on around 200 milliamps, 0.2 of an amp. It'll run less. It might require more voltage. These are rated at 400 volts, and I can put out roughly 175 volts, which is plenty for the plate of a tube to go, for a vacuum tube to go into emission and produce a radio signal to test the battery. Now, obviously, if I'm testing an AC/DC radio, they run on 110 volts AC or 110 volts DC. This power supply would produce that with no problem. If I'm running a DC only radio, well then, you know, I can drop the voltage down. I can use this for logic circuits. I don't need to. I have a 5 volt power supply, and a 12 volt power supply, but I can drop this down to 5 volts, and it'll be a stable 5 volts. If I want to maintain the voltage, I can put a Zener diode in here and maintain voltages, but I don't need to do that. This is a variable diode, and it's very dependable way of getting DC out of a variable AC main supply using an isolation transformer and a Variac. So if you need a DC power supply and you're set up for AC with isolation transformer and autotransformer or Variac, here is your way to develop that. Just pick up a few diodes. You want to have a load. If you don't have a load, you're going to have crazy numbers, as we've seen earlier. They're really there, so you don't want to come across these terminals when it says you got 150 volts across there, even though you're not driving anything yet. When you attach a ground line from your scope, you're going to have that voltage there. Now, it's not a lot of current, but it's there. It can still shock you. So if you build this circuit, you're doing it at your own discretion. But as long as you got a load on there and you got this inside a case or whatever, so that you just have outputs, terminals that you can connect to, you got a really good DC power supply. And all you need is a small filtering capacitor, because this rectifier is pretty efficient. If you want, you can increase the value of that, but you don't need to. 10 microfarads is fine, but you could put 2 and have 2 side by side, or a 22 microfarad capacitor, but 10 works fine. As you've seen on the scope, it got rid of all the ripple, and these diodes, they can handle the power that you need. So there you have it, a very stable output in a very powerful DC power supply. It'll deliver the power you need to run tube radios or even battery-powered electronics. Thanks for watching the video. If you liked it, please subscribe to my videos and share it as you see appropriately. Thank you.